Hello everyone, and thanks for watching Edupedia World Videos. This is the second video on the topic of planes in 3D geometry, and in this video we'll discuss some particular properties of planes. So in the previous video we saw how to write the equation of a unique plane in 3 or 4 different ways. The intercept form, when we are given that it is passing through a particular point perpendicular to line, the distance from the origin and the perpendicular direction, as well as 3 separate points. Now we look at some properties of planes and see how we are able to determine some more things. So the first thing we look at is the equation of a plane passing through the intersection of 2 given planes. So let's say we are given 2 planes. This would be the first one. Let's say this is the second one, P1 and P2. They're both infinite planes and they meet at this line, they intersect at this line. Then there could be a number of planes which encompass this particular line. You could have a plane like this. You could have a plane like this. There could be many different planes passing through this particular line. So that is our goal. Given 2 planes P1 and P2, we want to find out all the planes which will pass through the intersection of these 2 planes. So let's use the most normal form for the equation. Say P1 is given by R dot n1 cap is equal to d1 and P2 is given by R dot n2 cap is equal to d2. So these are the 2 planes. Now let's take a random point which has a position vector t, say, and that point lies on this line, which is the intersection of these 2 planes, which means that point satisfies the first equation as well as the second equation. So that point t satisfies t dot n1 is equal to d1, and it also satisfies t dot n2 is equal to d2. So if it satisfies both these 2 equations, we can multiply just the second one by lambda and add it to the first one, and what we get is t dot n1 plus lambda times t dot n2 is equal to d1 plus lambda d2. And now this is satisfied by every point on this line. But we can write this equation further as t dot n1 plus lambda n2 is equal to d1 plus lambda d2. Now this is t dot a vector is equal to some number, so this is basically an equation of a plane. And this is an equation of a plane of every point of which satisfies the equation, which means it encompasses this line. Now we change the value of lambda, we'll get a new plane. Lambda is equal to 0 would give me this plane. Lambda is equal to infinity actually would give me this plane. Lambda is equal to 5 or 7 might give me this particular plane. So this would basically be the equation, and this can further be written. Now we'll replace it by r. So r dot n1 plus lambda n2 is equal to d1 plus lambda d2. This is the equation. Now one mistake which sometimes students might make here, they'll think that this is the unit vector and this is the distance from the origin. That's not true, because if n1 and n2 are unit vectors, that does not necessarily mean n1 plus lambda l2 will also be a unit vector, right? So it could be a unit vector which would be a form of the direction cosines, or it could just have the direction ratios. And if you were to write this in terms of Cartesian coordinates, let's say the first plane P1 was given as a1x plus b1y plus c1z is equal to d1. Or The general form generally is minus d1. Minus d1 is equal to 0. And let's say the plane P2. By the way, some books refer to planes as pi1 and pi2 instead of P1 and P2. A2x plus B2y plus C2z minus D2 is equal to 0. So if these are the two equations of two planes, then a plane which passes through the line of intersection of these two planes would simply be A1x plus B1y plus C1z minus D1 plus lambda times A2x plus B2y plus C2z minus D2 is equal to 0, which basically is x times A1 plus lambda A2 plus y times B1 plus lambda B2 plus z times C1 plus lambda C2 minus D1 plus lambda D2 is equal to 0. Right. So this would be the equation in terms of the Cartesian coordinates. We know A1, B1. So yeah, we know A1, B1, C1 and D1. We also know A2, B2, C2 and D2. And lambda would be the parameter. As we change lambda, we get new and new planes. Now let's look at whether or not two lines are coplanar. Now two lines which intersect will always be coplanar, but two lines which are skewed do not need to intersect and they may not be coplanar either. So we are generally looking at skew lines because otherwise two lines will always be coplanar as long as they intersect. So let's say the first line L1 is given to us to be R is equal to A1 plus lambda B1. Don't forget the equation of the line. This is an equation of a line passing through A1 and parallel to B1. L2 R is equal to A2 plus lambda B2. Now let's assume for a second that these lines are coplanar. If these lines are coplanar and they are not parallel, then B1 is not parallel to B2, but the line perpendicular to both B1 and B2 will be B1 cross B2. And if we divide it by the unit vector, we don't need to, but if we do, it will make it easier. Then this would be n cap, where n cap would be the line perpendicular to both of them. So if L1 and L2 are coplanar, then obviously B1 and B2 are two lines which lie in a plane. B1 cross B2 will be perpendicular to both the lines, meaning perpendicular to the plane, and dividing by the magnitude we get the unit vector perpendicular to the plane. Right. Now A1 and A2 pass through this. So A1 minus A2 should also lie in the same plane. And if A1 minus A2 lies in the plane, then A1 minus A2 will be perpendicular to this vector because this is perpendicular to the plane. So what we have is A1 minus A2 dot n cap is 0. And now we can remove the denominator. So the condition that two lines are coplanar is A1 minus A2 dot B1 cross B2 is equal to 0. There will be a divided by mod B1 mod B2 as well, but we don't really need that anymore. Right. Now from this we can see, let's look at the Cartesian form. Let's say A1 is equal to x1 I cap plus y1 j cap plus z1 k cap, and A2 is equal to x2 I cap plus y2 j cap plus z2 k cap. And let's say B1 is given to us to be L1 I cap plus M1 j cap plus N1 k cap, and obviously B2 is L2 I plus M2 j plus N2 k. Then this equation can be written as, because the triple product is basically the determinant, A1 minus A2 gives me x1 minus x2, y1 minus y2, z1 minus z2, and here you have L1, M1, N1, L2, M2, N2. This is equal to 0. So this is the equation. If this equation is true, then these two lines belong in the same plane, otherwise they do not belong in the same plane. The next property we'd like to look at is the angle between two planes. Now, even though two planes do intersect at a line and we can somehow define the angle between them, it's actually much more convenient to define the angle between two planes to be the same as, or equal to would be the mathematical way of writing it, the angle between the two normals. So we want to find the angle between two planes. All that we do is find the vector perpendicular to the first plane, that is called the normal to the first plane or the perpendicular direction of the first plane. Similarly, find the perpendicular direction of the second plane, and we already know how to find the angle between two three-dimensional vectors, so that's what we'll do. So let's say the first plane is given to us to be r dot n1 is equal to d1. By the way, if it's not given in this form, we've studied many forms, you should know by now how to convert between one form and another so that you can always get any form of a plane in this form. Say the second plane is given to be r dot n2 is equal to d2. Then the angle between these two planes will simply be the same as the angle between n1 cap and n2 cap. And what is the angle between n1 cap and n2 cap? Well, n1 cap dot n2 cap divided by mod n1 cap mod n2 cap is equal to cos theta. Since n1 and n2 are unit vectors, this is simply n1 cap dot n2 cap. Right. Now, if instead of this we were given the Cartesian form of the planes, let's say a1x plus 1y plus c1z plus d1 is equal to 0, a2x plus b2y plus c2z plus d2 is equal to 0. So now here is an important point. Either we can take n1 vector to be a1 i cap plus b1 j cap plus c1 k cap, or we can take n1 unit vector where we'll have to divide it by the magnitude. Right. So this is actually valid for n1 vector also if we take the direction ratios in terms of the direction cosine, but then the denominator does not become 1. So this and similarly n2 we can write. So this tells me cos theta is equal to n1 dot n2, that is a1 a2 plus b1 b2 plus c1 c2 divided by this term mod n1 mod n2, a1 square plus b1 square plus c1 square into root of a2 square plus b2 square plus c2 square. And once again from this we can see that two planes are perpendicular if cos theta is 0 because theta is 90, which means a1 a2 plus b1 b2 plus c1 c2 is equal to 0. This means the two planes are perpendicular, and if a1 by b1 equals a2 by b2 equals a3 by b3, my mistake, a1 by a2, sorry, a1 by a2 equals b1 by b2 equals c1 by c2. This means that the two planes are parallel to each other. Right, so this is how we can find the angle between any two planes. And let's look at a few more properties. One is the distance of a point from a plane. And by the distance we always mean the perpendicular distance of a point from a plane. So let's say this is a point which we have point P, and then we have a plane like this, plane let's say P1. So we want to, this point P can have a lots of, in fact this probably extends to infinity. So this point P can have many vectors at different points in the plane, but one of them will be perpendicular to the plane, which means for one of them this line will be the same as the normal vector to the plane. That is what we need to find out, and eventually the perpendicular distance. Right, so this is just some random distance, and let's say there would be a perpendicular distance where the line would be along the normal. What we'll do is, we'll draw one of the perpendicular vectors from this plane which passes through the origin. This is 90, let's say. This point we'll call N. And what we'll do is, we'll draw a plane parallel to P1 but passing through P. Right, so we'll draw another plane. This is a plane which is parallel to the plane P1 but passes through P. Let's say position P has the point P has a position vector A, and P1, the equation is r dot n cap is equal to D. Now what that means is, if this is O, On is D, and the direction On vector, On unit vector is basically n cap. Right, r dot n cap is D. Now what is the equation of the plane, and by this line is D, On, right, the distance from the origin. What is the equation of the plane passing through P and parallel to this? Well, in that case, n cap will still be the same, but it passes through A, so we'll use the second form, passing through a point and a perpendicular direction. What we'll have is r minus A dot n cap is equal to 0. We've seen in the previous video. Means r dot n cap is equal to A dot n cap. Now what that means is, if this intersects this plane at point n dash, O n dash is equal to mod of A dot n cap, because now this is of the form r dot n cap is equal to A. So we know O n dash, and we also know O n, which is D, small d rather. So from that we can get n dash, which will basically be the same as the perpendicular from here, and that will come out to be D minus A dot n cap. So this is the final answer for the perpendicular. If one, now we know all three. The distance of a point with position vector A from a plane which is given in this form. So we know A, we know D, we know n cap. We know A, we know D, we know n cap. So this is the answer. Now we can write it in a few more easier forms. One, what if we are given r dot n cap, n vector is equal to D? Now in this case, this is not a unit vector and this is not the distance from the origin. But we can always write this as r dot n cap is equal to D. And now at this point, we can write n vector as n cap into mod n. So this will be by mod n. And in that case, the answer will simply be D by mod n minus A dot, and n cap once again will be n by mod n. So D minus A dot n by mod n. So if it is given in this form, this is the answer. If it is given in this form, then this is the answer. And now for a second, let's just see how it will look in the Cartesian form. Let's say the point is given to us to be x1 I cap plus y1 j cap plus z1 k cap. And the equation is given to us to be ax plus by plus cz is equal to D, let's say. Now this is not a unit vector, so we'll have to use the second equation. So what we'll get is, it's D minus A dot n cap. So ai plus bj plus ck dot x1i plus y1j plus z1k. So a1x minus b1y minus c1z, and divided by mod of n cap, that is root of a square plus b square plus c square. So this would be the answer if we have everything in terms of the Cartesian form. Now there is one final thing left in planes, and then this video will be over, and that is to find out the angle between a line and a plane. So once again, we define the angle between a line and a plane similar to the angle between two planes. What we do is, we find out the angle between the line and the normal, and we subtract 90 degrees from that. So it is defined as, or it is equal to the complement. We know what the complement is. The complement of 30 degrees would be 60 degrees. Complement of the angle between the line and the normal. So if theta is the angle between the line and the perpendicular direction of the plane, the angle between the line and the plane is defined to be 90 minus theta. The reasoning for that is basically, let's say this is the normal and we have a line like this. If this angle is theta, if we take the projection of the line parallel to the plane, this will be 90 minus theta. So now we can find theta easily. Let's say the line is given to us to be r is equal to a plus lambda b, and the plane is given to us to be r dot n cap is equal to d. From that, what we can get is the angle cos theta. Now this is the vector b, this is the vector n cap. So b dot n cap by mod b. Mod n cap is once again 1. So this is the angle theta. We want 90 minus theta. Let's call this alpha. So if this is cos theta, this is sine of alpha. From that, what we get is alpha is equal to sine inverse of b dot n cap by mod b. Or it can also be written if we have the form r dot n vector is equal to d, where n vector is of the direction ratios, not the direction cosine. We would get sine inverse of b dot n vector by mod b mod n vector. This completes all of three-dimensional geometry, lines, planes, and before that the direction cosines of a line. Thank you.